Hello, welcome to CSC 7013 Advanced Math for Computer Scientists. This is Brady Chen. Today, we're going to talk about Module 7, Finite Automata. The theory of automata is a theoretical branch of computer science and mathematics. It is the study of abstract machines and the computation problems that can be solved using these machines. The abstract machine is called the automata. Now here are the learning objectives. We'll first talk about the theory of automata, also known as theory of computation. And then we're going to define a finite automaton. So then we're going to talk about some examples of deterministic finite automata. So now let's define a finite automata. So a finite automata consists of the following 5 elements we called 5 tuple. Okay, the first element is the set of states, and this set of states must be finite. Okay, and then the second one is a set of input symbols. For example, you can say 0, 1 or A, B, C. Okay, it's a set of input symbols. And then Q0 is the initial state. The finite automata must start from the initial state. And then you're going to move to the next state based on certain condition. Now, which next state you're going to move to is based on the criteria we set up in the finite automata. And then F is a set of final states. Remember, the finite automata can actually accept a string, and then this is the input, and then we're going to start from the first state, initial state, Q0, and then based on the element in the input, we're going to decide which is next state we're going to move to. Okay, and then what's the next state we're going to move to, and eventually we're going to end up a final state. Okay, that final state could be something called accepting state. That means we accept the string because that string reached that state. That's acceptable. Now, the final state could be a rejecting state. So that means you reach that state. So that means this input is rejected. Now, most of the finite state machine or finite automata may have more than one final state. Okay, so F basically represents the set of final states. Now delta, it's called a transition function. Okay, it basically defines, from based on the input at each state. Now, what's the criteria? We define the criteria, so that means based on the input, which next state we're gonna move to. Okay, that defines that's called the transition function. Now, let's actually move to the next slide. So we're gonna actually use a lot of examples to illustrate this concept. So let's discuss the components for the finite automata. Okay, the first one is the input, right? A finite automata must have an input. The input is a string fed to the machine, which the machine will determine whether it is part of the language that the machine was designed for. Remember, the string could be, 0101. Okay, so the purpose for the finite automata is to determine whether this string satisfies the criteria, so it's part of the language we define, right? So the string must only be made up of symbol from the machine's alphabet. That's one of the 5 tuples we talk about in the definition of finite automata, right? Normally we use sigma to represent this alphabet. Okay. Now the string must contain only the symbols from the sigma. So for example, sigma contains 0, 1. So then the string must be a sequence of 0 or 1. Okay. Now the second component is called return. Once the import is fed to the finite automata, and the finite automata can actually move from one state to the other and eventually reach the final state. Now, if the final state is accepting the import, then you're going to return accept, right? Or you're going to actually reject. So the results of running the machine on given import, that's called a return. So initially, this will either be accepted or rejected. So if the finite automata eventually, move from one state to the others and eventually landed in the final state, which is accepting state, then the import is accepted. If reached the rejecting state, then it's rejected. Now that's a return. Okay. The other component is a state, right? State is a resting place while the machine reads more import. So once the import is actually fed to the finite automata, the finite automata going to read each of the import symbol. Okay. Now it based on the current import symbols and the current state. Then it will select the next state. Okay, so the status is a resting place while the machine reads more import. Now, if more import is available, so it just reads one import, and that's the last import. It's the last symbol in the import. Now here is the start state. Again, it's one of the 5 elements or 5 tuple. Q0, right? If you check the previous slide, it's Q0. Now, for programmers, this is known as the program entry point. If you start a Python or Java, you always start the entry point. Normally, the entry point is in the main program. It's the first statement in the main program, right? In Java, it could be in the main, MAIN. Okay, so it's the state that the machine naturally starts in before it reads more import. Okay, so that's start state. Now, the other component is called accepting state. Okay. Now, accepting state is the final state. Okay, it contains a set of states which the machine may halt in, provided that it has no import left. So if you machine start the finite automata accept the import, which consists of sequence of symbols, right? It read the first symbol and combined with the initial start state, it just reaches the next state. Okay, and then it just read the second symbol combined with the current state it is resting in, right, and determine the next state. So then the finite state machine keep reading the symbols in the import until it reaches the end of the import string. Okay. So accepting state basically means, so when the finite state moves from one state to the other, it eventually reaches the accepting state, which is good. That means the import is part of a language, and we accepted the import, right? Now, another state is called a rejecting state. So it's any state in the machine which is not denoted as the accepting state. So that means the string is only rejected if the machine halts in a rejecting state with no more import left. So we reach the end of the import, but sorry, you are actually eventually landed in the rejecting state. So we rejected that import. Okay. So this is basically what the finite automata, does. Accept the import based on the rule, decide whether this import is accepted or rejected. Now, the dead state, it's a kind of state, but sometimes it's called a trap state. It's a rejecting state that is essentially a dead end. So that means if we have an import, right? The import could be a string of symbols. Now the import goes into the finite automata, and with the start state, let's say A is a start state. And then you basically read the first import. Okay, the first import is 0. Okay, so let's say, okay, it's a 0, and then we're going to move to another state B. Now the next state is 1. Based on the rule, we're going to move to another state C. And that next one is 0, then we move to D. Okay. Now next state is 1 again. The import is 1 again. And then based on the 1 combined with the current state D, we're going to decide which is the next state. Okay. The next state could be another state, which is not A, B, and C, but it could be, the previous already used state. Okay, if next one's 1, then we have to move back to B. And then the next one's 1 again. So based on rule, if it's 1, then we go to C, right? And then if the next one's 1, then now the current state is C. Now we haven't defined that yet, but it could be another one. Say if the current state is C, but the import is 1, like we actually mentioned here, then you go to E. So we can just keep going until we reach the last state, which is, say, F. Okay. Now, if when we reach a state F, it's a dead state. For example, if we reach the end, it's a dead state. However, now we reach a rejecting state. Rejecting state is not necessarily a dead state. It's just that we reach that state and we have no more import, right? Okay. So if for another state, it could be, if we have another import, which is longer, then it could be actually, we can be actually out of the rejecting state. So if you reach the rejecting state, and then we only say this import is rejected. But doesn't necessarily mean every string, if we actually at the middle of somewhere it reached the rejecting state, and if we have more import symbol, then there's a way we can be out of the rejecting state, and we were back to normal, and we eventually end with the accepting state. Now the dead state is different. If you somehow reach G, a dead state. Now, if we have 0, 1, 0, and then for dead state, then there's no way to be out of dead state. Okay, so which means for the rejecting state, it could be like, okay, if the next import value is 1, then we'll be back to the previous state. Okay, okay, if it's 0, we can be all the way to B. Okay, so there's a chance that from B we can still actually move forward to the accepting state. But for the dead state, that means, okay, if the next import value is 1, then we end up in the same state. If next import is 0, we also end up with the same state. So we're trapped. So once we reach the G, no matter what's the follow-up symbols in the import, we will never be able to get out of G. So that G is the dead state. Okay, so we're going to check this with more examples. And the other component is called transition. It's a way for a machine to go from one state to another given a symbol from the import. So transition is defined as just like a function. So transition delta is defined saying what's the current state and what's the current import symbol. By the combination of current state and import symbol, and we define what's the next state we're going to go. That's basically defined as like a function. So transition may even point back to the same state that they have come from. Okay. Now in this case, we call it a loop. Like in this case, we move here. Let me actually use different colors so you can see it clearly. So if we reach that point, okay, then we move next, and then we move next, and then based on the value which is 1, right, and also the current state, the current state is F, the value is import symbol is 1, then we're going to move back to B, right? So that means the state F combined with the import symbol, then we will go back to the state B. So it can actually move back, and that's called a loop. Okay. So we know by definition, finite automata has 5 tuple, 5 elements. Q, okay, which is a set of states and a set of symbol, initial state, and a set of final state, and the transition delta, right? These are 5 elements. Now, FA is characterized into 2 types. There are 2 types of FA, the finite automata. One is called deterministic finite automata. Now the other one is called non-deterministic finite automata. And for deterministic finite automata, we use DFA, and the other one is NFA. Now we will actually talk about both of these 2 types. Okay, let's move forward. Let's talk about deterministic finite automata, DFA. Now by definition, a DFA is 5 tuple, Q, sigma, Q0, T, and oh, I'm sorry, it's F and the delta. Okay, so Q is the finite set of n states. That's the same as general definition for the finite automata. Actually, the first 4 tuples, first 4 elements are basically the same, as the general finite automata. Now, the only difference between deterministic finite automata and non-deterministic finite automata, NFA, is the transition function. the last element. Okay, the first four are basically the same. Now sigma is the alphabet of import symbol, and the Q is the special start state. Of course, Q0 is the start state, which belongs to the general finite set of Q. So it's a subset of, it belongs to the set of states. F is a set of accepting states, okay, or final states. Again, F is a subset of Q. So now here's the definition for delta, the transition function. So for deterministic finite automata, delta is a transition function that maps a state and a symbol to state. So that means if we have a finite automata, let's say this is a finite automata, okay. Now this is the start state. Okay, we start from here. Here's intermediate state, and the D is we call the final state. So now here's the transition function. The transition function basically says, now given the state, let's say state A, now combine the current symbol, okay, current symbol, for example 0, and then we will map to B. So that means if the current symbol is 0, we're going to map to B. Now if the current state is A, but the current state symbol is 1, we're going to map to C. Okay. And then we have to define the delta for each state, right? So for example, if delta B, if the delta, B, if the current is 0, we're going to map to D. Now if the current state is 1, if it's 0, current state is 0, we map to D, right? That's basically what it says. Now, if the current state is 1, we map to what? We haven't defined that yet. Now, there's a couple of different possibilities. If the current state is 1, the current state is B, and the value, the symbol is 1, then we could map to D as well, right? In this case, we're going to say, okay, for 1, 0, and 1, we both map to D. Okay, that's okay. That could be the case. But it could be something else, saying if the current state is 1, we're going to map to C. Okay. We can do anything we want, right? So then, now we're going to define the delta for, like, if its current state is C, if it's 0, we're going to map to D. If the current state is C, if the value, the symbol is 1, we map to D as well. So then, both 1, 0, and 1, we map to D. Okay. Now, for D, then we're going to define the delta for D, right? Let's find some free space. We can write this definition. Let's say I can just squeeze that space. So delta D0 equals what? Delta D1 equals what? Right? If delta 0, then we're going to say, okay, if it's 0, we map back to B. If it's 1, we map back to C. So then if it's 0, we map back to B. If it's 1, the current state is D. The current value is 1. We map back to C. Now that's a complete definition of the transaction function, right? Then we can decide if given us, import 0110, whether this import will be accepted by this finite automata or not, right? Let's check. So the starting point is A. The first import is 0, so we're gonna actually, move from A because the value is 0, and the starting point is A. So based on the transition function, it's A and a 0, right? A and a 0. So you're gonna move to B, right? Now we check the state which is B, and then the second import is 1, so we have a B and a 1, B and a 1. So then we can have a B and a 1, so we're going to move to C. Now C, we check the C, and then the import symbol is 1 again, right? Now, so we have a current state C, and the import value is 1. Then we're going to check the C and a 1, which goes to D, right? Okay. Now, the current state is D, and the last value is 0. Okay, the symbol is 0. So we have a D0, right? So the D0, that's the first one, D0, which actually goes all the way, D and the 0, which goes all the way to back to B. Okay. So this finite automata will actually take this import 0110, and eventually it will reach B at the very end because there's no more import. Now, if B is not the accepting state, then we're going to reject this one. If B is the accepting state, then we accept it. Now, suppose in this case, D is the accepting state. D is the only accepting state, the final state. Then we will reject this. Okay. So this example is not really clearly written because we have small space, but we will actually take more examples. Now, normally for the transaction function, we're going to actually write as delta, that's the function name, and here's the Q, that's the state, and sigma, that's the symbol, right? So Q, that's the Cartesian product. So Q times sigma, that means that the delta going to accept a two import value. One is the state, the other one is the symbol. And then you're going to decide what's the next state you're going to go. Okay, so that's the delta. This is actually a kind of math notation. So in the DFA, the deterministic finite automata, for a particular import character, let's say 1, the machine goes to only one state. Okay, so that means if it starts from the current state A and the import character is 1, then the transition function has to define what's the next state to go. So the transition function is defined on every state and every import. So that means if the current state is A, the current actual import is 1, then the transition function delta has to define what is the next state. If it's B, then it's B. Okay. There's no ambiguity here. So, which means in DFA, null or epsilon, that means the empty move is not allowed. Or in another word, DFA cannot change state without any import character. So that means the current state is A, and there's no import, and then it transfers to next state. That's not allowed. Now, later on, when we talk about non-deterministic finite automata, we'll find out, the change could be like a random. Okay. So here's how we're going to execute our finite automata on the import sequence as follows. So if for the deterministic finite automata, DFA. So let's start with the start state, right? So if the next import character matches the label on the transition from the current state. So let's say current state is A. Okay, the transition, the label on the transition is 1 goes to B. 0 goes to C. So that's a label. Okay, that's a label. Now if the next import character, okay, so if that's the start state, that means the next import character is the first character, right? Then that's if that character, the import character is 1, okay. From the current state, the label says 1 goes, if the label is 1, it goes to state B, label 0 goes to state C, then the next import matches the label on the transition from the current state to the new state. Okay, now that means this import matches this label, right? This import 1 matches the label 1. So then from the current state A, we go to B. That's defined. Now if the current import is 0, and then it matches the other label 0, then A gonna goes to C. Okay. So to decide which state we will go, it will actually check both the current state and the current import. Okay. Now we continue with this transaction on each import character. So the next character is 0, and next, then we're gonna actually check what the finite, state machine actually defines. What's the next label for state B? Okay. If no move is possible, then stop. And if accepting state, then accept. Okay. Let's actually check. Okay, so let's warm ourselves up again with the terminology. So we say alphabet is the set sigma, right? Which contains all the symbols for the finite automata. Okay, so in this case, sigma is A, B, C, and D. Okay, so these A, B, C, and D are symbols. Now the string could be, if the symbols are A, B, C, and D, the string could be C, A, B, C, A, D. Any combination of these symbols. It's a valid string on the alphabet set. Okay. Now here's another example. 011 0110 is a valid string on this set sigma equals 01. Okay. We cannot write AB101 out of the set sigma equals 01 because AB are not a valid symbol in this sigma. Now the length of string we also define as the number of symbols in the string. Okay. So in this case, S is 0110 and the length of string is 4. Okay. Now if the length is 0, it is called empty string. So we actually use either lambda or epsilon, okay, to represent the empty string. A finite automata can be represented graphically, known as state diagrams. Actually, we already used the state diagram in the previous slides, but let's actually formally define the state diagram. Okay, we use circle with the name inside to represent the state. So typically in this example, I normally use circle and capital letter to represent the state. If you look at the other textbook, or if you search for any information about the financial automata online, you might see some people use, 1, 2, 3, 4 to represent the state. That's okay. But here, we always use A, B, and C, or D, E, F, G, or whatever. So we use the English capital letters to represent the state. And the letters inside the circle, that's the state. Now the arcs labeled with import alphabet show the transaction. So if we define, say, here's the state A, and here's the state B, okay, 2 states, and then that's the arc labeled with import alphabet. Supposedly the alphabet we use is 1, 2, right? If we define the set of symbol, which is 0 and 1. Okay, I'm sorry, it's not a 1, 2, it's 0 and 1. And then, so then the arc labeled with either 0, or then arc labeled with 1. This is actually define the transition. So the transition has two elements. One is the state, okay, and the other one is the label. Label has to be one of the symbol defined in the set of symbols. So the label could be, that's arch label, and coming originally from the state A, and the label 1 originally from the state A. And then, based on the current state A and the label, we actually uniquely define what's the next state, which is B. If it's A combined with 0, that's B. A combined with 1, that's C. Okay, that basically defines the transition function. So the arcs labeled with the import alphabet shows the transition. Okay, the initial state, the start state, is denoted by empty single incoming arch. So normally we use, the incoming arch. It's coming from nowhere. Okay, so there's nothing before the arch. So that means A is the start state. Okay. Now the final state is indicated by double circle. So let's say we define the financial automata. So B combined with 0 goes to D, and B combined with 1 goes back to A. That's okay. That's totally legitimate. And then C combined with 1 goes to D, and C combined with 0 goes to B. And D combined with 1 come back to B. That's okay. And D, if it's 0, goes back to C. That's okay. So that defines the transition for each value of D, and the label, it defines what's the next state. And then if D is the final state, we pretty much actually use the double circles. So that means this is a final state. So now this is a complete financial automata. And actually it's a deterministic financial automata, because for each state and each import value, then the next state is uniquely defined. So that's deterministic financial automata. Now let's define the non-deterministic financial automata, DFA. Oh, I'm sorry, it's a NFA. That's a mistake. I need to correct this. NFA is similar to DFA. It looks similar, but it's very different. Okay. It's similar to DFA, except the following additional feature. This following additional feature makes a huge difference. Number one, in NFA, null or epsilon move is allowed. So that means in the non-deterministic finite automata, it can move forward without reading symbols. That's interesting. So let's suppose we have a current state A. Now A can move to state B without reading any symbol. Okay. So the second one is it can transit to any number of states for a particular import. Okay. So that means if the current state is A, now if the import is 0, then it can move to B, okay, or it can move to C. Or it can even actually move back to A. That's kind of weird, right? So now our current state is A, and the import value is 0, and A combined with 0, then what's the next state? I don't know. I don't know what's the next state, but I can tell you what's the possibility. Which could be the possible next state? So the possible next state could be A, could be B, could be C. That's the reason why we call it non-deterministic finite automata. Okay, it sounds weird, right? But it is a finite state machine. It's a finite automata, and it has its advantage and disadvantage. So these above feature don't add any power to the non-deterministic finite automata. If we compare both in terms of power, both are equivalent. Okay, so due to the above additional feature, NFA has different transition function. Okay, the transition function is different. Everything else is the same. It has the same number of, it has a Q, which is a set of the states, and it has the sigma, which is the alphabet, which is a set of the symbols, and it has a starting state, and it has a final state. But the transition function is different. So instead of like for the DFA, the transition functions uniquely define what's the next state. But in the non-deterministic finite automata, transition function can be written as this. So we have a current state and import character. The import characters could be coming from the set of symbols. Like if sigma is 0 and 1. So it can be, delta could be, from A to 0, from A to 1. And it also can from A to epsilon, which is empty, which is the null actually state. Oh, no, I'm sorry, which is a null symbol, which is empty symbol. There's no symbol. Okay. So that's why it's a sigma times epsilon. It could be, sigma or the epsilon. Now, which potential state the transition function you're going to move to is also uncertain. But it might be any of the state. Okay, so potentially it could be 2 to the q. Okay, if we actually use the, two symbols, sigma, it's going to be 2 to the q. The q is the number of states. What does that mean? We're going to talk about this in the next, module. So in this particular module, we are not going to talk about the NFA. We only discuss DFA in this module. Okay, we're only going to focus on the examples of DFA. But in our next module, we're going to focus on the NFA.